24. Large language models. So you probably knew this was coming. You can imagine it was kind of foreseeable at this point. But yeah, in November of 2022, OpenAI introduced ChatGPT to the world, and suddenly everyone and their best friend was doing some combination of the following four things. Number one, writing news articles about how the advent of AI means we will all be unemployed and leads to the rise of Skynet. As you know, the system goes online August 4th, 1997. Human decisions are removed from strategic defense. Skynet begins to learn at a geometric rate. It becomes self-aware at 2:14 a.m. Eastern Time, August 29th. And as you know, in that movie, anybody not wearing 2 million sunblock has a really bad day. So lots of people wrote articles about why this is definitely going to happen, and that's what AI means, and we are all doomed. Reaction number two was, I'm going to start a startup that uses ChatGPT to do something B2B/B2C SaaS something profit, which is basically a light wrapper around ChatGPT, by feeding it this and sort of asking it to do things for you. Which obviously is pretty hard to defend. Like, anybody can do that. Like, what you're looking at here is not that special. Number three, if you have the misfortune of looking at LinkedIn frequently, you would have seen a lot of people suddenly describing themselves as prompt engineering experts, which I'm really good at rephrasing my question 15 times until I get the answer that I want from ChatGPT. Like, there is thought that needs to go into how do you prompt it, or like what question do you ask to solicit the right answer, but calling it prompt engineering, I feel, kind of gives it a certain amount of like legitimacy that is normally associated with civil engineering is for building buildings. Prompt engineering, like, you're just writing your sentence in a good way. Like, this is strange. But perhaps my least favorite, if you go and again should look at LinkedIn, but also on other social media and stuff as well, generating lots of what I would describe as extreme cringe content about how to get rich easily. Right, so here's my video. Buy my course, and you too can make $1 bajillion a day. Passive income. You don't have to have any knowledge, experience, what have you. And I've looked at some of these, and they're all silly. There's things like, well, you can just get like ChatGPT to write books, and then sell those books on Amazon, and it didn't cost you anything. And thanks, I hate it. So there's a lot of that, and the thing that should tip you off that this isn't real is if you could actually make a ton of money, selling books that ChatGPT or something writes for you. Why would you tell other people this? Why would you want them to do the same thing? Because there's a limited pool of people who are looking to buy random books on Amazon to see if they're any good, and why should they give your money to a competitor? Right? What they're actually selling is the video or the system, or there'll be your startup mentor or whatever, and that's not going to work. Right? Selling courses is profitable somehow, but the technique that they're trying to teach you in there isn't going to do it. There is linked in the notes a video on the subject of what are described as get rich easy schemes. In the past there was more of a tendency towards get rich quick, right? Do this and you'll be a millionaire in 5 years or 5 weeks or 5 months, or whatever sounds good at the time. But people sort of know that get rich quick schemes aren't real at this point. Skepticism is pretty high, so that's not going to work. So the new trend is towards get rich easy. It's not instant, but you don't have to work very hard. And unfortunately, it's kind of not like that. Okay, all this aside, right? Why were these sort of the reactions? It's not that large language models are totally new. Certainly these things have existed before. People have used them, created them, and machine learning or something is not a field that was invented by the OpenAI consortium and all of that. It's not that new. But ChatGPT ended up a hit because it was very publicly available and is fairly what I would describe as conversational. That you can like ask it a question and it will answer you in something that seems kind of convincing for how another person might hypothetically write. Now whether they actually write like that or not is a different subject, but it is better than it sounds like a robot. And this is what we would describe as natural language processing, sometimes abbreviated NLP. And in the words of some experts, source linked in the notes, these models are trained on massive amounts of text data and are able to generate human-like text, answer questions, or complete other language-related tasks with high accuracy. Now listen, this isn't the only kind of like large language model that exists. Lots of them exist. There are also many different kinds of machine learning systems out there, and you are most likely familiar with at least some of them. Ones that identify is this a bicycle or a traffic light or something. Those exist, and when you have to prove that you're human by clicking on all bicycles or something, right? Like there's a secret like I'm training the AI in how to recognize what does a bicycle look like in Google Street View. But there's lots of stuff out there that we would refer to as a large language model or other machine learning. Now, just because your large language model gives you an answer doesn't mean it's true or correct. You may enjoy this legal video, ChatGPT fail, about a lawyer who used ChatGPT for research, and research heavily in quotation marks there, because they were trying to make the point on some case, and they wanted ChatGPT to, I guess, do their homework for them and write up their argument. Here's the thing, though. The system returned an answer. So ChatGPT did give an explanation, and it did provide citations. The problem is the citations are completely made up, right? ChatGPT is actually not very good at math, for example, because it has an understanding of what a math equation looks like. One number and then a plus sign and then another number and then an equal sign and then yet a third number. But it doesn't actually do the math because it doesn't understand the meaning of these things. So yeah, this is concerning, right? The system returned an answer with completely made up references, which then the lawyers submitted as an official court filing, and as you can imagine, the judge was not impressed. Not even a little bit. So the video itself is kind of long. It's about 30 minutes, and some aspects of that you would find a little bit redundant as people who are perhaps more technically inclined than the general purpose audience of the legal channel. But nevertheless, there is kind of a good overview of sort of what this is and what went wrong, and why the lawyers in this case are facing sanctions, which is just fancy lawyer speak for you're in big trouble. So the problem that we face is what are referred to as hallucinations. And hallucinations are what happens when the system just makes up something. Like the large language model returns you an answer, but the answer is made up, it's not true, or it's incorrect or inconsistent in some way. And all of these things are subject to that sort of problem, right? You do still have to verify that whatever you got from the system is correct. Right. This shouldn't be super surprising if you remember like a concepts course around the subject of engineering. One of the things that was probably emphasized is that in the practice of engineering, legally and professionally, the engineer is responsible for understanding how a given tool works and verifying that the output is reasonable or correct. And certainly when I was a 1A student, the canonical example that appeared in the textbook was something along the lines of, if a civil engineer uses some software and the software says, yeah, the building is fine, but it actually is not and it falls down, the civil engineer is still legally and professionally liable because it was their responsibility to verify that the output of the tool was correct. They can't just say, well, the computer program told me this would be fine, right? They have to understand, is that reasonable, is that correct? And if it's not, right, then don't build that building. Don't do it. It's not going to work. And yeah, it's rare, but not impossible, I suppose, that people who are not doing their professional duty end up sent to jail, which of course you do not want. Now, part of what makes the models that we're talking about, sort of at the time of writing this lecture and recording it, GPT-3 and 4 are the models that are kind of currently in use. 3 and 3.5 in general availability, and 4 if you ask nicely and you get sort of some pre-exposure. It is entirely possible by the time you're watching this, everybody's using GPT-4 or 5 or 7 or what have you. So part of what makes it work is this idea of pre-training, and in fact in GPT, the P and T stand for pre-training, and this is actually kind of an interesting thing to examine, right? This course is not on neural networks, and it's not really focused on large language models. I mean, we're like 2/3 of the way into the course at this point, so I hope you figured that out. Nor is there going to be like a big pivot of like, actually we've deleted the next 12 lectures and we're just going to focus on this. But there is actually kind of an interesting conversation to have here around the idea of, well, if we're going to train a system, can we do that better? Can we do it faster? Can we do it more efficiently? Or can we get better results by using a different approach? And there is actually sort of something to that, right? Because we're training a large language model on what is effectively a very large data set. Think of OpenAI sort of scraping the available internet to find stuff to feed to their training models. Okay, well that's a lot of data, and generating or updating such a model is computationally challenging, so performance is relevant. It is worth talking about here. So before we get into that, I want to talk a little bit about parameters. And one factor that we can use to understand a model is the number of parameters. And this is a way to measure how good the model is at responding to requests. And to sort of explain a little bit about why it matters, this is just LLM AI models are generally compared by the number of parameters, where bigger is usually better. The number of parameters is a measure of the size and complexity of the model. The more parameters a model has, the more data it can process, learn from, and generate. However, having more parameters also means having more computational and memory resources and potential for overfitting and underfitting the data. Parameters are learned or updated during the training process by using an optimization algorithm that tries to minimize the error or the loss between the predicted and actual outputs. By adjusting the parameters, the model can improve its performance and accuracy on a given task or domain. Okay, yes, this, as you may imagine from sort of how I read it, was a quote from a Microsoft online paper about sort of how do parameters work. Again, source linked in the notes. So we're not really going to be inventing our own models here. We're not going to do anything that crosses too far into the subject of what would be a machine learning type course. But maybe we can tune some options, and maybe there's sort of some interesting ideas here that do intersect with the main content of this course. So let's try some optimization. And this section is based on a guide from a website called Hugging Face, which describes itself as an AI community that wants to democratize the technology. And the guide in question that we're going to follow is based on using methods and tools for training using one GPU. There do exist multi-GPU kind of training systems, but for the sake of keeping things simpler for first pass, then we'll just sort of focus on one GPU system for now. Now, you may have guessed by the placement of this topic in the course material that in fact the GPU is a good choice for how to generate or train a large language model. You probably knew that already, even before it was mentioned, but certainly if not, it's like, why are we talking about it now? It's because it's connected. Just don't confuse Hugging Face with face hugger. Word order matters here. Okay, why a GPU? That's that's sort of the interesting question, right? In this case, we're talking about transformers, not Autobots assemble kind of transformers, but you could be forgiven for thinking so. But there are three main groups of optimizations that happen. There are tensor contractions, statistical normalizations, and element-wise operators. What are these? Well, contractions involve matrix-matrix multiplication, and that's the most computationally challenging part of the transform. Statistical normalizations are a mapping and reduction operation. And then element-wise operators are things like dropout, biases, and they themselves are not particularly computationally intensive. Okay, but that's kind of interesting, right? We don't need to really repeat the reasoning as to why GPUs are good at matrix-matrix multiplication, nor why they're good at sort of map-reduce kind of operations, because we've covered that already. But by putting it in those terms, I think you can see why GPUs are a good choice for this sort of thing, as opposed to doing it with the CPU. There's no law that says you can't do it with the CPU, it's just not very efficient. So let's not do that. In discussing the optimizations that we are going to make, we also need to consider what is in memory. It is possible that whatever we want to do is limited by available memory as opposed to the CPU time or the CPU power that we have. That's going to be what we call foreshadowing, because that will actually play a role a little bit later on. Yeah, the number of parameters that we have is going to influence how much memory we're going to use, and if we're trying to use too much memory, we may not be able to actually accomplish the training that we intend to do. Okay, so there's two kinds of optimizations when we think about how do you optimize an LLM, and I have to make a decision about what we want to do in this case. So one kind of optimization is we want to make a model that gives answers quickly, right? That is interesting, and that is something that you want if you are trying to make it an interactive approach. You were making ChatGPT and you want to, it takes questions and then returns results. And it seems sort of conversational, then being able to generate answers quickly is important. Maybe even more important in the case of something like GitHub Copilot or some other coding assistance tool, because in that situation what you want to do is produce relevant suggestions quickly enough that the user looks at that and says, yes, I accept this suggestion, as opposed to it's taking too long, whatever, I'm just going to write it myself. So that sort of thing does make a difference. But the other kind of optimization when I talk about optimizing is how can we generate or train the model efficiently? And that's kind of more fun maybe than it sounds, but let's think about it, right? So the first thing, when we're making a fast model, right, this touches on a bunch of things that we've talked about already in this course. So could we use more space to reduce CPU usage, right? We're trading space for time. This is a fairly common operation, and we could do that. Are we willing to speculate? Are we willing to settle for a less precise answer in terms of getting it quickly? Those sorts of things, we know what to do. When we talk about speculation, though, the last time we covered this, we were saying, all right, we're going to value speculates. We're going to imagine that this computation most likely returns the value of 900, and we're going to go on that basis. But when we start speculating sort of in the realm of natural language processing, it starts to get a little bit more fun, because instead of speculating what's the answer going to be, now you're trying to guess what's the next question going to be, right? And in guessing about what question somebody's going to ask, this is actually kind of doable, right? There's probably a fair amount of predictability in this, and I mean you won't always get it right, but people generally are predictable, and there are certain answers that sort of lend themselves to follow-up questions fairly easily. And I was interviewing somebody, and they told a story about this, and the obvious follow-up question was how did users like this? And then the question after that was what metrics did you have to validate that this was effective? Those are very predictable questions, so you could speculate that the user might ask those. Okay, but let me just sort of take a step back before we kind of get to the question of how we would sort of generate or train the model efficiently, and talk about why. Why do you want to generate or customize an LLM rather than use an existing one? I mean, existing ones do exist, and why do you have to worry about it? Well, to start with, you might not want to send your data, and it may be sensitive, to OpenAI, for example, for ChatGPT. That might not be what you want. There are some checkboxes maybe in configuration where you can like opt out of certain things, whereas don't use this for training, but like, how sure are you that they actually do that? Right? Like, you just kind of have to take their word for it, don't you? And should you take their word for it? At the time of recording, the CEO of OpenAI has just been let go for, I think they described it as not being consistently honest with the board. So how much do you really trust them? So yeah, that's maybe a concern that you want to avoid by making sure that the data never sort of leaves your systems. That may be also more important in other jurisdictions where it's like a privacy concern to send your data to a different country that may or may not have the same privacy laws. I'm looking at GDPR, for example, as a reason why this might be more difficult. Another idea is the intention to specialize for your workload. Generating a model or refining an existing one can make more sense where you get better results by sort of focusing in on just the kind of thing that you need. To illustrate what I mean, ChatGPT is very general purpose. You can ask it to make you a Dungeons and Dragons campaign setting, and it will do that, but you don't need that functionality if you're trying to ask it to analyze what customer behaviors are the ones that are most likely going to result in upgrading their plan, right? The extra capability, parameters, and what have you takes up space, uses computational time, and it's kind of wasted because you shouldn't be asking it to make you a Dungeons and Dragons campaign setting on company time, and certainly on company money, right? If you're paying ChatGPT for usage, this starts to hurt. So maybe specializing for your workload makes sense. A smaller model that gives better answers is more efficient. So the first major optimization, and something we want to talk about first, because it's probably the easiest to do, is the batch size. And the batch size is just a way of telling the GPU, this is how much I want you to do at once. And this isn't really super exciting as a configuration parameter, but we'll see what we can do with it. It's a little bit like when we discussed the idea of more threads to increase performance, right? At some point, increasing the batch size probably doesn't help. Because you have sort of more workers active, and if resources were idle, then those workers can use those resources. But if there's not enough work to do, or there's other resource conflicts, at some point just adding more threads didn't help anymore, and we'd be looking at something similar. Okay, so the code here is a little bit too large for the slides, so what I actually want to do is sort of go over it in the code editor. And we use an example also from Hugging Face with some light modifications to sort of see what we can do with a very simple example using dummy data. The thing we're going to look at is in Python. A lot of LLM machine learning content is, but if you're unfamiliar with Python, it's okay. Python is relatively understandable as languages, and we'll talk through it. So don't feel bad if you're not feeling super confident in Python. You don't have to learn Python for this course. Just trust me that we'll go through it, and it should be pretty comprehensible at the end. The model that we're going to use is called BERT Large Uncased, and the model itself is about 340 megabytes in size, and that's not a particularly large one. It's trained on a bunch of English language data, and it's uncased because it makes no distinction between capitals and lowercase letters, so it sees Word with capital W and Word with lowercase w as equivalent. So let's take a look at the code. Okay, so we're going to just take a brief look at the code here in a simple example. And there's a bunch of imports here. Uses PyTorch for actually running it, if you're familiar with that at all. But it's one of the common libraries for working with large language models in Python. And we will define some default arguments. We're just going to put stuff in a temporary directory. The evaluation strategy here is set to no, so there isn't one. We'll do one training epoch, we'll log with levels, and reporting is none. So there's a couple of functions defined here as well. Print GPU utilization, which will just sort of tell you about how much GPU memory has been used by this model at this time. So we will get device 0, and we will read the index, read the info from it, and then GPU memory that's occupied will be printed, sort of divided by 1024, and we're all set. And then there's also something that prints summary, which tells us sort of how long it ran and how many samples we trained per second based on the metrics. So once we get started and actually executing it, we will look at sort of what is the initial GPU utilization. We expect it to be basically 0 at the beginning of execution. If it's not for some reason, that means that like something is also using the GPU at this time, which we probably do not want. And so that's just kind of like a warning sign that something is out of whack, and we need to terminate that other process before we continue. And then we will do the initialization with Torch, and we can see how much GPU is consumed by starting that. We will then load the model, see how much GPU memory has been occupied, and then we will set the verbosity level to error, unsurprising. And then we will generate a bunch of dummy data where we're just going to generate some random numbers and some random labels, and we will turn it into a Python dictionary and send it in. We will send in our training args to, if we're looking here at line 4950, we are configuring our training arguments, we send them in, we start the trainer, and then we print a summary of the result. So let's take a look. Now, when I wrote this code, the first thing I tried to do was run it on my laptop, but that failed because my laptop does not have an NVIDIA GPU. So expecting this to work was kind of silly, and I should have known that before I got started. But that's how it is. Anyway, let's try it ECE Tesla 0, shall we? So when we start up, initial GPU utilization is 0, which is good. That's where we expect it to be. It indicates nothing else is using the GPU at the time, which is the situation that we want to start from. Otherwise, like I say, something needs adjusting. Once we've initialized Torch, the current GPU utilization goes up to 417 megabytes. Okay. It tells us that some things were not initialized in the model. All right, nothing too scary there. And we should probably train the model, yes. And then once we've loaded the model, we are at 1,705 megabytes of memory used. And then we actually try to train it for real. Then we run into a CUDA out of memory error. We tried to allocate 20 megabytes. That itself is not bad, but it's just sort of the last straw here because there's 7.4 gigabytes total capacity, and we've already used 6.9 gigabytes, and 16 megs are currently free. So yeah. ECE Tesla 0 ran out of memory trying to process what is ultimately a very small model. Okay, well, what's going on here? So I asked NVIDIA SMI, which is just like a tool that will tell you about GPU usage and whatnot, and I learned that the card has only 7,611 megabytes of VRAM available, and truth be told, that doesn't seem like a lot for what we're trying to do. It's not like this is a tiny amount of memory. It's not like we can do nothing with it, but it feels bad. Like the model that we want to train, it doesn't seem that complicated. It doesn't really feel like there's all that much to it. And here we are saying, well, it's out of memory. We can't do this. Okay. So, now what, right? Let's look at what we saw in the code, and you might have spotted that in the code, what we asked for originally was a batch size of 4. It's possible that like a batch size of 4 is just too much to do in parallel, and we're not gonna be able to do that much, so it would make sense to reduce it. So I reduced the batch size to 2, did not help. Reduced it to 1, did not help. So, in the words of Captain Kirk, we need more power, Scotty. Like, what we have is just not adequate to the task. And I looked around at the other ECE run GPU servers that we had on hand at the time that I was doing this, and we didn't have anything bigger. Right? Lab staff were trying to buy some more cards, and you may have them at this point, or there may be more LLM focused machines that are available to be used at the time. But at the time of recording, there was nothing. So what do we do? What do we do? Correct answer is change to a smaller version of the model. If we were actually seriously invested in running the model that we wanted to run, then maybe like this is a problem and we can't actually do this. But for the purposes of just a demo, it's okay if we use the smaller model. So I used a smaller version, which is called BERT-base uncased, and it is only about 110 megabytes, and that is something that the card can actually handle. So let's go with that. So here's the output of batch size 1. And again, when we start up, our initial memory utilization is 0. Once we've loaded Torch, that hasn't changed. And it's still 417 megabytes. And then once we actually get started, we're training the model, we run it, and we have some statistics to report. We can see memory occupied goes up to 887 when it's loaded. It takes 109.6 seconds. And we see loss numbers, learning rate, epoch, training runtime, samples per second, what have you. And total GPU memory occupied was 3,281 megabytes. All right, that's something. It is a result. It is a result. I need to experiment a little bit more with batch size to try to find what is ideal for this GPU. And this takes a while, as you can imagine, because if you look at the times, it's 109 seconds for run and 85, and so on. So every one of these is 1 to 2 minutes of execution time. So playing around with the different sizes takes effort and has a fair amount of waiting for it to be done. So I'll spare you watching the console, wishing it were done. So with batch size of 1, it took 109.6 seconds. With batch size of 2, 85.82. With 4, 72.18. With 8, 66.70. And you can see the utilization of the GPU memory, which I've really just calculated as a basis of when it tells me the memory used at the end, divided by what we know to be the total capacity of this card, 7,611 available megabytes. And yeah, utilization climbs pretty significantly, and unsurprisingly, choosing a batch size is 9. It's going to result in out of memory. So the other nice thing about this is the out of memory is encountered very quickly on startup, so it's fairly straightforward to like binary search different batch sizes to find out what is the maximum that you can process in one go. 4 seems too small, choose 24, see what happens, and you can binary search. It is nice in a way that the out of memory occurs much faster than waiting for the results to come at the end. So it's easy to tell when we're just not going to succeed with this batch size. Okay, so that's one way to increase the performance of our model. We do seem to be kind of memory limited though, right? It feels like if we could find a way to make the model like use less memory, then we could maybe increase the batch size. And I mean, if we look at the table of execution time, right, increasing the batch size does seem to decrease the execution time, right? By reducing it from 109.6 seconds to 66.7 seconds, like that's actually a significant increase in performance. It's not magic, it's not 10x or anything, but like this all counts, right? The bigger the model, the more complicated it is, the longer it's going to take to train. If you can cut it in half or reduce it by 30% or something, like that's still a significant increase, and if you're paying for CPU time, or GPU time I should say, that's big money. So yeah, why not? So let's think about what we could do to reduce memory usage. How do we squeeze a little more performance out of this? And I should also add at this point that focusing on the memory utilization side of things is part of what makes this topic a little bit different from other topics that we've covered in the course. Most other topics in the course have been much more compute focused, but focusing on reducing memory usage is a little bit newer. So the first idea that we're going to try is gradient accumulation. And gradient accumulation is, what we're going to do is calculate gradients in small increments rather than the whole batch. And in doing so, this kind of has an effect of changing the effective batch size. It does increase the number of compute steps, because instead of like summing up all the data sort of in one pass, what we're doing is creating a bunch of smaller sums, then we have to revisit them and integrate them. But that's okay. And what we're effectively saying is we're willing to trade some CPU time for memory. We're going to reduce memory usage at the cost of increasing compute time, and we hope that results in a net benefit because it increases the effective batch size. Okay, so with gradient accumulation, I was able to play around a little bit here, and I kept batch size fixed at 8 just for the purposes of comparison. And the first one with steps is 1 was kind of our baseline. That's what we were doing before because we didn't use gradient accumulation in that. And 2, 4, 8, 16, even I was doubling it, as you can tell. And when I got to 32, it's like, all right, I want to see how far I can push this. And yeah, I mean, you can see sort of the difference between 128 and 62 is almost negligible. And in fact, we're very quickly into the decimal points of time improvements. But we are increasing the samples per second most of the time. There is a bit of a downward trend from 1024 to 4096, which is kind of interesting to interrogate, but we are making a little bit of progress. It feels like we have some benefit here from doing this. Increasing samples per second, even by a small amount, certainly for a much larger data set, feels like it would be beneficial, right? Every bit counts. Every minute is precious. Every second may have financial cost associated with it. But this table made me suspicious. Does anybody know why? Okay, so when we got to 128 for gradient accumulation, there was kind of a drop-off in memory usage. And you can look at the utilization. It went from like 98.7 to 87.2. And this made me think about sort of other indicators. Like, what am I missing here? Like, what's going wrong? So the output also talks about training loss, and you might have seen that in the sample output that we were talking about sort of with dummy data, where it shows the loss numbers, and with gradient accumulation step of 1, loss is 0.029. With 2, it's 0.070, and it increases for a while, and then it decreases, and isn't that concerning? Is this loss meaningful? Is it a lot? Is it a little? Does it matter? And you see, you might have been screaming this, at your screen the whole time. Maybe all of this has been like, obvious to you all along the way. But the thing is, we're not really paying attention to whether we're doing a good or a bad job here, and that's weird, because what we actually need is some validation, right? You can train a model and you can ask the model to make a prediction or what have you, but if we never check whether it does it correctly or not, it's a little bit like, well, did you do your homework? Yes, but we're not going to check if the answers were right or wrong. And you would probably like to know if it doesn't have to be for marks, but you would like to know at least, did I solve this circuit problem correctly, so that when the exam does come, I'll know if I get the marks or if I missed something. So we need validation. Right? We need some way of checking what's going to happen. And the example we've been doing so far has been quite literally random data. So we can't just validate by dividing our work into a training set and an evaluation set, because it's all trash anyway. We need something else. We need a different data set. Okay, so that's what we'll do. We need to use a different thing, and what we're going to look at is Yelp data. Why? It's all because it's available from another guide from Hugging Face, and it's suitable for our purposes. Yelp, if you're not familiar with this, is the website that struggling restaurant owners blame for ruining their gourmet burger place that charges you $22 for an unimpressive reheated Cisco hamburger with no side dish. And where people go on to post such beautiful reviews as the one by Sarah L here about how she won't shop there anymore because they won't let her in after closing. Yeah, please don't shop there anymore. Okay, so like when we have this, right, we actually have some more possibility of having an idea of whether what we're doing is working or not, because we can have a training set and we can have a validation set, and that's what we're gonna do. So the Python code that we're going to look at is significantly different, but again, I'm going to show it in the code editor because it's just kind of impractical to show it all in the slides. We'll take a look. I skipped some intermediate results in the results table, which we'll come back to because it takes like 9 minutes to calculate, and doing it for every individual size obviously feels kind of inefficient. But let's look at the code editor and we'll see where we end up. Now, I should make mention of the fact that all this code appears in GitHub repository. It appears under this lecture topic in the live coding directory, so if this is a little bit small or otherwise difficult to read, then you can always follow along using that. But yeah, we have a number of imports. It's still based on sort of the same basic premise. It's just kind of a modification of what we saw earlier. So we have a new function here, tokenize, which will split up some example input into tokens. Print GPU utilization hasn't changed. Defining the compute metrics function will again sort of show you how we did. And then print summary is the same as it was before. The example code that this comes from, sort of on Hugging Face, didn't have quite everything, but I copied over some things from the dummy data example just to make sure that the results were a bit more comparable, and that I would have a better idea of like what does it actually mean when we talk about how much CPU memory we're using, making sure we have consistent metrics for this. So once we get into the actual execution code of here, not just function definitions, we are again printing the GPU utilization at the start so we can look at it. We will initialize torch. We will load our Yelp review full data set and use the tokenizer. And then we will create our training data set and our evaluation data set. And the training data set is going to be just using the elements that we want to send into the model so we can teach it effectively. And then the evaluation data set is to check and see, did we do a good job in terms of successfully training it. Now, in this case, we selected like 1,000 of them, and we select somewhat pseudo-randomly using the seed value 42 and all of this. It is not super realistic for how you would actually train such a model. What you would probably do is you'd have a much larger training set and a smaller validation set, but whatever. We just need some amount of understanding sort of how is our accuracy. Okay, so yeah, let's see what happens, right? We're going to then submit our training args. We're going to evaluate accuracy. We will run the trainer with our training data set or evaluation data set. We ask it to compute the metrics, and then at the end we print the summary. And you can, as I say, run this code. You do need, you probably want to do it on ECE Tesla 0 for apples to apples kind of comparison. But I'll show you the summary results table. So here's our results table as promised, and with gradient accumulation steps shown in the leftmost column. The time, as you can see, 500 and something seconds. So this is a lengthy process, and that's why I only show here the cases of 1832 and 1024, because again it was taking a long time to generate all the results. And yeah, when we look at our data, our samples per second doesn't change dramatically, except 32 cases an outlier, and its final accuracy numbers are 0.347, which seems kind of interesting, right? I ran the 32 case to sort of check a few times why did this one seem so different, and the one we see in the table is actually the best result from this, so that wasn't just like random bad luck or anything like that. This is kind of interesting, right? Like increasing the gradient accumulation does change the effective batch size, but maybe it's a little bit concerning because, well, getting the batch size too large means a limited ability to generalize. And this is what we would refer to as overfitting, the model effectively gets stuck in, say, a local maxima or minimum, and that isn't producing the results that we want, because we want something that's sort of flexible enough to generalize to whatever situation you are putting it to. But smaller batch size isn't better either, because underfitting is just sort of the mirror image problem. You get worse accuracy because your model says, well, maybe it happens, maybe it doesn't, right? To just sort of give very silly analogies, right? If you had like a weather prediction model that was like extremely underfitted, it would say everything is equally likely, who knows, the weather does whatever it wants. Cool, but not helpful, right? But an overfitting model would perhaps predict that like it will never ever snow, because the majority of the time it doesn't snow, so it just rules it out as a possibility, even though it's going to snow. That's just happening at some point. So yeah, that's kind of interesting, right? And in the ELP example, I get worse accuracy with batch size of 1 than 4, but 4 is worse than 8. There is no magic number where I can say choose these settings and everything will be good. So that doesn't feel nice. In the interest of time, we aren't able to experiment with absolutely everything, but there are kind of a few ideas that we could evaluate that might be interesting. So one of them is this idea of gradient checkpointing, which is sort of increasing compute time to save money. And instead of saving activations, well, we just save only some and we recompute the rest on the fly as we need. So this might allow us to work with a bigger model even when we have a somewhat limited memory card. Training takes longer. Now, according to Hugging Face, it might take something like 20% longer to actually execute this. By default, all activations on the forward pass are saved, so they can be used in the backward pass, but we could choose if we wanted to not save them and recompute them on the way. Compromises save some of them and recompute the rest, but does it work? Does it work? There's a lot of that in this. And the answer is maybe. So when I tried it out with a batch size of 8 and gradient accumulation turned off just to make things a bit more comparable, we did get slower. Time went from 66.7 seconds to 93.07 seconds, and the memory decreased from 7,069 down to 3,619 megabytes. So as expected, we did get slower, but we did use less memory. Maybe that means we can use that to increase the batch size, and raising batch size actually 16 meant the total time to completion was 100.55 seconds, but still only 3,731 megabytes. So increasing the batch size to finish a lot faster might help, but maybe it's not great, right? Using checkpointing even with batch size of 1 is not sufficient to run the BERT large uncased model on ECE Tesla 0, and cranking up the batch size to a very large number, although it might give you an answer faster, maybe it isn't actually a better answer. So it is possible that we just would rather not do that, period. Right? There's no obvious benefit from doing this. We'd have to experiment and make a determination about whether it is actually sensible to make that change. we'll see. Excessively large batch sizes can make it worse. There's a couple of other ideas suggested that I didn't really play around with, but we could certainly do them in a general purpose scenario, and one in which we had more time. One of them is mixed precision, so using less accurate types, and this is a pretty straightforward trade-off of accuracy for time. The default for most things is going to be 32-bit floating point numbers, but if we don't need that level of precision, some of the 32-bit types can be replaced with 16-bit ones, and that can increase our speed without really meaningfully losing any precision in our calculations. Another idea is data preloading. It doesn't seem to be the case in the code that we're working with, but hypothetically, if you felt that the limiting factor was getting data to the GPU, you might remember from like an operating systems course that maybe you took, pinned memory is pages of memory where the operating system is instructed not to swap those pages to disk for faster access. So we could ask for that, which would make it a little bit easier to transfer data to the GPU when we need it. Another idea is multiple threads in terms of loading data and getting it to the GPU, but that's not super interesting at this point because we know all about this. This is by no means exhaustive. The Hugging Face Guide talks about a lot of things that we simply do not have time to go into. Mixture of experts, which very deep into the details and beyond what we want to cover here. But one possibility is, could we buy a bigger GPU? Can we throw money at this problem? Could certainly help. It's not necessarily a guarantee, and again, at the time of writing, GPU cards can be hard to come by. But it is an idea. Could we use a multi-GPU system so we could get more parallelism? Probably. Again, we would have to have a system that we could put multiple GPUs in and convince them to get along, which may be challenging. But a lot of things that we know from the CPU domain also work here. So let's wrap up this topic and just to close with sort of a couple of interesting thoughts. More than most other topics that we've talked about so far, the LLM topic really does show a lot of the inherent trade-offs in optimizing things. Do we trade memory for time? Do we trade accuracy for time? Do we trade memory for CPU, so do something that's more computationally intensive but uses less memory, or vice versa? These things are not necessarily obvious, and we're often forced to make these choices now in a way that maybe we weren't with other problem domains, where it's like, it doesn't matter, we can have the best of both. Another thing that's kind of interesting to consider is if we are training our model, like how much accuracy do we need? And if we want to do this, do we err on the side of overfitting or underfitting? There's no obvious answer for every situation. You will have to make a decision based on the problem that you're facing and sort of what are the costs of getting it wrong in either direction. I think it's fair to say that the technologies that we use for this and the decision making around it will get a lot more sophisticated. That we will figure out ways to trade accuracy and get a lot more time, or even get improvement without losing any accuracy. We will also have much better recommendations about like what we should be doing and what we should not be doing. These kinds of things are still all very early days. And we haven't quite figured out all the details yet. And this is normal when sort of new technologies are created, that we haven't quite figured out what works and what doesn't. And you can look at early airplane designs, and you can see sort of people working out, we'll try this, we'll try that, before we end up settling on certain conventions or certain choices that seem to be, if not optimal, then at least well agreed upon. And adequate for the purpose. So in the meantime, though, we can have a lot of fun experimenting and learning. It's like a fun and interesting and exciting area, and this is not the kind of field in which you, as someone who's about to graduate, will feel you're at like a huge disadvantage against somebody who's been doing this exact thing for 30 years. All of this is relatively new, or was at least very niche until recently. So there will be a lot of opportunity for people to get into this sort of field without there being this sort of high barrier of entry of people who were doing it for 10 years before you were even born. So yeah, I encourage you to experiment around with it a little bit and have some fun with it, and hopefully you find a little bit of the joy of experimentation in this.